Okay, I'm going to talk you through this animation here of DNA replication. Before we start it off, I just want to talk about DNA replication in general. So this process, DNA replication, occurs only once in the life of a cell when a cell realizes or gets a message that it's going to have to divide into two cells. So before it can divide into two, it needs to take all of its DNA and make an extra copy of everything, so that when the cell does divide into two separate cells, both of the cells that are made have a complete set of everything you need. So before the cell can divide into two, it needs to make a copy of every single one of its chromosomes. So it's got two of every single one, so that when the cell divides, one set can go to this side and one set can go to that side. So that's why a cell would need to do this process. It's, again, only happens one time in the life of a cell, just before the cell is preparing to divide itself into two. So let's get this going here. All right, hold on a second. I'm going to rethink this so I can see what I'm doing. Okay. All right. So the first thing that happens is we see the DNA strand and looking like a double helix, and we are going to have to separate the two sides of the DNA to be able to open it up like a zipper to access the base pairs, which are in here. I don't think you can see my pointer. So that we can build the new piece of DNA that's going to line up. So this first green blob that's coming in is an enzyme called helicase, and helicase's job is to unzip the DNA like the head of a zipper. And you're going to end up with two helicases, one pushing to the unzipping to the right and one unzipping to the left. So there's going to be helicases on both sides. In this animation, you're only going to see one of them because we're just going to focus on the one side of this little piece of DNA that we're prying apart. Where you start to pry the DNA apart, that's called the origin of replication. So the origin is where everything started, so it's sort of the middle of the bubble. And then where the DNA is actually being unzippered, where the helicase is sitting, that's called the replication fork. So I wish you could see my pointer, but I don't think you can. The origin of replication is the middle of the bubble, and the replication fork is the two sides of the bubble where the helicase is sitting. So there goes the helicase, unzipping the DNA along and creating that replication fork. Now, what happens next is the DNA doesn't like to be unzipped like that particularly. It's much more stable when it's zippered back up together. Those bases like to make pairs with each other. They like to line up. And so as soon as the helicase has unzipped them, they try and stick back together again, like with their hydrogen bonds, because they're attracted to each other. So to stop the DNA from zippering itself back together, these little black blobs, and we're going to call those single strand binding proteins, or SSBPs, they're going to come in and they're going to kind of coat all the way along the DNA to stop it from being able to sit back together. It's going to keep the two sides apart. So here comes our SSBPs to save the day, to stop that DNA from sticking itself back together. All right, so now we've got everything prepared. We've got the DNA unzippered, we've got it protected from going back together. So now we need to actually start building DNA. But unfortunately, the enzyme that we use to build DNA, which is called DNA polymerase 3, that enzyme cannot just work from scratch. It can't just come along and just start making DNA on a template. There's many reasons why. One of the main reasons is that it has to have an OH group to build nucleotides onto, and there's nothing there to build onto. It's just a blank slate right now. So we need to get things started. And to get things started, we're going to use a different enzyme. And the enzyme that gets everything started is called primase. So we're going to have some primase come in here. It's going to look like a big pink blob. It's an enzyme. All right. And we know that it's an enzyme because its name ends in A's. So this big pink thing looks like big pink lips. is an enzyme, and its name is primase, and its job is to build a little short piece of nucleic acid to start off this whole process. It's kind of getting it primed, like you prime a pump to get things going. Now, although we're trying to make DNA here, we're trying to build a strand of DNA, for some reason primase doesn't make DNA, it makes RNA. So those little red T's that you can see coming in, those T's aren't T's, they represent nucleotides, and the primase is hooking together nucleotides to line up with the bases on the template. And as the nucleotides are hooked together, a short strand is made. It's going to be red, but it's made of RNA nucleotides. So there's going to be U's in there, and the sugar along the backbone is going to be ribose instead of deoxyribose. But we're going to have to handle that, so because it's the best we can do. So here's our primase, and there we go. It made us a short little piece of nucleic acid going from a 5 to 3 direction, sitting on our template. So now what we've created here is an end. At the very end of that little strand, the animation shows it 4 bases long. In real life, it's closer to maybe 10 or 20 bases long. But once you've got that made, now you've got an end sitting there ready for the DNA polymerase, which is the enzyme you really want to be using, because it's going to build DNA, which is what you really want, to come and build the DNA that you need. So once the primase has made its little starter piece, it's going to fall off. And then the DNA polymerase, and it's called DNA polymerase 3, is going to come in, and it can start elongating that little piece. And it's going to use the nucleotides that have G's and A's and C's and T's, and it's going to use the sugar deoxyribose. So it's going to make proper DNA going on here. So let's watch it go for a bit. And you can see it's adding on to the end that the primase left behind. And as the polymerase moves along, it just kind of muscles the single strand binding proteins out of the way so it can access the template DNA and fill in the strand. All right, so the first little red bit was the RNA primer made by the primase, and then the pale greenish blue is the new DNA that the DNA polymerase 3 built. And you can see you always build by adding on to a 3' end. That's why the arrow is pointing towards the 3' end. We're adding. That piece is getting longer and longer towards the green blob of helicase that's at the replication fork. Now remember, this is always moving, so that green blob is moving off to the right, opening up more and more template as the DNA behind it is getting filled in. This is called the leading strand. We'll talk about why in just a bit. And now we've made our DNA. So I'm going to play that through one more time. First of all, we find the origin, we pry apart the DNA, and then here comes the helicase to unzipper the DNA like that. Now, as soon as the DNA is apart, it doesn't like that. It's going to try and zipper itself back together. But to stop that, we're going to coat it with these single strand binding proteins. Now those are in place. The primase can come in to get everything started. The primase is an enzyme. Here it comes. It's going to start to build a short little piece of RNA to create that 3' end. That little piece is called the primer. And now you've got a 3' end, which the DNA polymerase 3 can use as a starting point to then build the actual piece of DNA that we want. And as the DNA polymerase 3 chugs along, it's going to build, knock the single strand binding proteins out of the way, and just carry on behind the helicase as the helicase opens up more and more template. That's the synthesis of the leading strand.